Hello, and welcome to the self-paced course for building your own deep research agent. My name is Edward. I'm a technical marketing engineer at NVIDIA, and I'll be your host for today as we walk through this course together. By the end of this course, you will achieve a better understanding of the foundations of AI agents, retrieval-augmented generation systems, or RAG, and how you can deploy and utilize deep research in your enterprise. Without further ado, let's dive right in. Let's talk briefly about the agenda. We'll first introduce the fundamentals and motivation behind deep research, including a quick demo of what you'll eventually build in this course. We'll then cover an overview of the course and talk about the course logistics. Namely, we'll be building up our deep researcher from the fundamentals over a series of 4 notebooks, where each notebook builds on the concepts introduced in the prior notebook. Finally, we'll wrap up with some helpful resources and next steps. Alright, let's first briefly introduce and set the background for deep research. Deep researchers are essentially a next step in the evolution of large language models, or LLMs. You may already be quite familiar with the box on the left, which represents a general-purpose LLM. Users can ask queries and get back fairly decent responses with general-purpose information. For example, I might want to know about robots, and the response I get back can address my query quite well. The next step up is that middle box, which represents connecting my LLM into my own real-time knowledge base instead of relying on general pre-trained knowledge acquired at training time. This enables augmented knowledge through a process called retrieval-augmented generation, or RAG. Now, in addition to general-purpose knowledge, I've now equipped my LLM with the ability to retrieve valuable context from my own personal data sources, meaning I can now ask more powerful queries like, tell me about our robot. The RAG system can retrieve context specific to my robot and use that information to inform its generated response instead of just relying on general-purpose knowledge, which can get me a much more specific, useful, and actionable response. Finally, we can move into the world of deep research here on the right. Research agents can perform complex, multi-step research by autonomously searching, analyzing, and synthesizing information from various different sources to create comprehensive and well-grounded reports. This differs from RAG in that instead of providing single-shot responses, research agents can now act as more powerful, autonomous systems that incorporate 1. Agentic planning to break down more complex tasks and queries into a multi-step plan, 2. Agentic tool calling to complete tasks with custom tools and data, and 3. Agentic reasoning to provide iterative refinement and self-reflection before returning a response. We can now ask complex queries requiring comprehensive synthesis across multiple data sources, such as, how will our robot do in this broader market? This query requires a multi-step approach that is difficult to complete with single-shot RAG, such as needing to research about my particular robot, learning about the broader real-time market, and so on. In short, you can think of deep research as adding agentic capabilities to traditional RAG, to make it much more powerful and able to handle more complex, multi-step tasks effectively. Some of you may already be quite familiar with deep researchers, and maybe you've even tried some deep research SaaS offerings yourself. Deep researchers are available from many companies such as OpenAI's ChatGPT, Perplexity, Google's Gemini, and so on. But these solutions are managed by third parties and may not be appropriate for your enterprise. You may not be allowed to send your proprietary company information to these third parties, and these solutions may be hard to understand black boxes. These challenges can leave this powerful technique outside the grasp of your enterprise. So, how can we address this? Well, this is exactly what motivates our course, which is to teach you how to deploy your own deep researcher on-prem on your own infrastructure using an NVIDIA blueprint. This enables you access to and control over the code that you're deploying, helping you understand each step required. And since you can host this open and portable deep researcher on-prem, you can even use it with internal company documents and data without them ever leaving your organization. Hopefully, that is something that you can get excited about as we work through this course. If that's not exciting enough, here's a quick 2-minute demo of the final deep research agent you will build over the course of this curriculum. Alright, now that we know a little bit about what we're getting into, let's talk course logistics. This course is structured over 4 content notebooks, covering prerequisites, deploying a reasoning NIM, deploying a RAG pipeline, and finally deploying our research agent. Each notebook is generally structured as shown with an introduction section giving an overview, a section that covers motivation and concepts crucial to understanding the later code, a series of runnable code snippets, and an optional section for moving on-prem for eventual production deployments. Finally, we round out each notebook with a recap of learning and next steps. This is a self-paced course, so feel free to spend as much or as little time as you see fit on each of these notebooks. This course is hosted in Jupyter Lab as a development environment, and you can gain access to it via the Deep Learning Institute, or DLI. In terms of timing, expect between 30 minutes to an hour per notebook on average, though this can vary greatly from notebook to notebook and based on your own self-pacing of the content. Due to compute limitations, each notebook will utilize the NVIDIA-hosted model endpoints, but we include on-prem instructions as well if you would like to try hosting models locally at a later time. Finally, there is a video walkthrough that accompanies each notebook. Feel free to utilize that as a resource as you are working through this course. By the end of this course, you will master the concepts behind agentic AI, namely how agents can plan, execute, and iterate on complex tasks, leveraging NVIDIA Nemotron models and agentic reasoning and tool calling capabilities. You will also successfully deploy the NVIDIA RAG blueprint, successfully deploy the NVIDIA IQ Research Assistant blueprint, and ultimately get a better understanding of the production pathway for agents that you build. And once again, this course consists of 4 core content notebooks shown here. These notebooks start at the fundamentals and gradually build on each other cumulatively until we have built our final deep research agent. From understanding reasoning to building a RAG pipeline to combining the two in a deep research agent, you will see the step-by-step process of how you can build and deploy your own open and portable deep research agent. Notebook 1, Prerequisites. We begin our journey by gathering the prerequisite information we need to complete this course successfully. To do this, we need to generate our NVIDIA API key on NGC, which will help us authenticate into the NVIDIA-hosted model endpoints and the NGC container registry to pull down the containers that we need. Also, we need to generate the Tavily API key for the web search tool calling capability we want for our deep researcher later in this course. This should be a fairly quick and straightforward notebook to complete, but it's important to walk through these steps to see how you as a developer can get started with building your own AI projects. Notebook 2, Deploy NIM. With prerequisites gathered, we can now jump into the code. In this notebook, we will dive deeper into exploring agentic reasoning capabilities, especially with respect to the NVIDIA Nemotron family of open models. You will interact with chat interfaces to experience responses with and without reasoning enabled, interact with code to see how you can build in these models into your own AI applications, and finally learn about how to deploy NVIDIA NIM locally on-prem in addition to prototyping with the NVIDIA-hosted model endpoints. Part of what motivates this transition from generative AI to agentic AI is the expansion from 1 scaling law to 3 scaling laws. Historically, the scaling law of AI was simple. Bigger models plus more data equals better performance. While still effective, this approach has limitations and high costs. Today, we now recognize 3 distinct strategies for scaling AI capabilities: pre-training, post-training, and test time compute. Pre-training is like sending an AI model to college, where the model can learn a vast amount of general knowledge from a massive curriculum. To accomplish this, we can train a large model on a massive and diverse dataset, such as the entire internet. The model learns fundamental language properties, patterns, and general facts during this intensive, expensive, and compute-heavy phase, and emerges as a powerful, general-purpose foundation model with broad but relatively unspecialized knowledge. Post-training is like getting a mentor or an internship after college, where the model can refine the foundational knowledge for a specific job. To accomplish this, we can enhance a model's accuracy and relevance for a specific task, domain, or use case. For example, one key technique is fine-tuning a foundation model on domain-specific knowledge, resulting in a highly specialized, more refined model proficient in specific domains or aligned to tasks and use cases such as question answering or instruction following. Finally, we have test time scaling, which is like taking an open book exam, where the model is given extra time and resources to reason through a problem during inference before answering. To accomplish this, additional computation is allocated at inference time during the output generation, where the model can formulate a chain of thought and perform multiple reasoning passes to tackle complex multi-step problems. Recent research shows that for many tasks, especially dealing with complex reasoning, allocating compute at test time can be more effective and efficient than simply creating a larger pre-trained model. To summarize, a large pre-trained model serves as the foundation. Post-training aligns it with a specific domain or set of instructions. Then, at runtime, test time scaling methods are used to provide more compute for challenging, reasoning-intensive queries, leading to the best possible outcome. We will see firsthand how this test time scaling can continue to improve models beyond the traditionally recognized pre-training and fine-tuning scaling laws. Let's see what a model looks like without agentic reasoning learned from test time scaling. In this example, we are interacting with a Llama Nemotron Super V1 model and have toggled reasoning off. You can see that without reasoning, the model just provides an answer a single shot. And from the answer, the model seems to think that the word strawberry is spelled with only two R's, which is inaccurate. Now, let's see what the model looks like with this agentic reasoning toggled on during inference time. You can see now that the model completes a reasoning portion before returning the final response. While this takes a little longer, we get back a response that is much higher in quality and much more accurate than before. The model now counts the correct number of R's in the word strawberry after reasoning about it. This demonstrates the powerful capability that reasoning models can bring to agentic AI applications. You'll get to explore this more hands-on in this notebook, and hopefully you can see how powerful these reasoning models can be when powering agentic AI systems. Notebook 3, Deploy RAG. Once we have a solid understanding of what reasoning models are and how we can use them, let's see how we can connect them to data sources to help augment its knowledge. In this notebook, we first explore the foundational concepts behind RAG before deploying a working RAG pipeline with NVIDIA-hosted model endpoints. From here, we'll explore the API for both the ingestion and retrieval stages of the RAG workflow. We'll learn the ingestion API, understand the document retrieval and re-ranking processes under the hood, and experience an example of a response with RAG toggled off compared to a response with RAG toggled on. Finally, we'll introduce how to deploy the RAG pipeline we just built to run locally on-prem, much like the previous notebook. This is the architecture of the RAG pipeline we will build and deploy using the NVIDIA RAG blueprint. While complex, we can see this breaks down into two stages: extraction during the document ingestion phase, and retrieval during the document retrieval and response generation phase. To use the RAG pipeline, we must first ingest our documents into the vector database. Oftentimes, enterprise data is messy and unstructured and includes a variety of different modalities in addition to text. We can see multimodality is supported in this RAG pipeline that we'll build, and we will leverage NeMo Retriever and Paddle OCR to chunk and process text, images, infographics, charts, and tables before running them through an embedding model. Once the embeddings are generated, we will store those embeddings in a vector database for later retrieval. With documents stored in the vector database, a user can now use the RAG pipeline by submitting a query. This query gets processed and converted to embeddings compared to the stored document embeddings in the vector database using similarity search, and the more relevant documents are extracted and supplied to the language model as additional context for that original user query. The model can use this additional retrieved context to generate a higher quality response, reason and reflect on that response if needed, before forwarding that response back to the user. In this notebook, we will dive deep into a better understanding of concepts represented in this diagram, as well as take a hands-on approach to exploring this RAG architecture in code. Notebook 4, Deploy Researcher. We now have all the pieces we need to build our deep research agents. Let's see how we can put together what we learned in the previous notebooks to build this deep researcher. In this notebook, we first explore the foundational concepts behind deep research before deploying a working research assistant with the NVIDIA-hosted model endpoints. We'll also bulk ingest some sample data collections to the researcher's knowledge base to use for demonstration purposes. From here, we'll walk through step by step the deep research process, stopping at every stage to explain what is going on under the hood and how it helps improve the quality of the final generated report. We'll touch on concepts such as agentic reasoning, tool calling, and keeping humans in the loop. Once complete, we'll show you how to clean up the entire workflow, including both the research agent and the previous RAG pipeline. Finally, we'll introduce how to deploy the deep research agent we just built to run locally on-prem, much like in the previous notebooks. This is the architecture of the deep research pipeline we will build and deploy using the NVIDIA IQ Research Assistant blueprint. While complex, we can see that this breaks down into a few different major components: the reasoning model, the RAG component, and the web search component. The reasoning model should look familiar. We went over this in depth in Notebook 2. We will be using the same Llama Nemotron supermodel to empower the reasoning and planning capabilities of this agent. This enables the researcher to come up with a research plan with smaller subtasks, conduct and synthesize the research, reflect and iteratively improve the draft, and defer to human input when needed to refine the final draft of the generated report. The RAG portion should also look familiar. We went over this in depth in Notebook 3. We will be using the same RAG architecture, simplified here to fit on the slide. This will provide the research agent access to a private, self-hosted vector database with user-uploaded documents and enterprise data that may not necessarily be found publicly. And finally, the new component in this diagram here is the web search capability of the agent powered by Tavily Search. This represents an additional tool call that the agent can opt to take to help augment retrieved results with new information, in case the contents retrieved from the RAG database are deemed insufficient to properly answer the agent's self-generated queries. This can be toggled on or off by the user, but can enable greater flexibility and access to a wider set of sources beyond what is stored in the database, if desired by the user. The agent, as part of the refining and iterating process, can find gaps and generate new queries, and utilize either the information retrieved from the RAG database or information retrieved from the broader web to help synthesize and formulate the best possible response in response to the user's query. In this notebook, we will dive deep into better understanding the concepts represented in this diagram, as well as taking a hands-on approach to exploring this research assistant architecture in code. Alright, by now you should have a better understanding of the motivation and content path of this course. Let's wrap up with a few helpful resources and next steps. To learn more about the content presented in this course, feel free to check out the documentation for the NVIDIA NIM microservices, which we have leveraged extensively as part of this course, from understanding concepts behind agentic AI to deploying the actual blueprints. You can also learn more about the blueprints we deployed by visiting the GitHub repositories for both the RAG and the IQ Research Assistant blueprints. Finally, you can check out the additional DLI resources on the right, including the NVIDIA developer forums, where you can post and interact with other developers just like you. NVIDIA's Deep Learning Institute offers a wide assortment of interactive courses on AI, accelerated computing, and accelerated data science, as well as professional certifications on topics like agentic AI, deep learning, and more. Hopefully, you find this course engaging, useful, and ultimately enjoyable as you work through the curriculum. Happy learning!